video is for Math 116, and this is the last assignment that we'll have for winter term. And this is section 4.3 in the textbook on combinations and permutations as well, but this sort of introduces the concept of a combination. So a combination is a selection where the order is not important. And over on page, 133, I mentioned that you can remember that because on a combination pizza, it doesn't matter which toppings you put on, what order the toppings go on, whereas in a permutation, it is important. So the combination is where the order is not important. So we build the definition for a combination off of the definition for a permutation, and I go over this on page 132, where if we were choosing 3 people from a group of 7 to serve on a committee as president, vice president, and treasurer. So there it's not so much the order, well, I mean you could call it order, but it's the assignment of a particular role to each of those 3 people, okay? So that differentiates any of the choices where the same 3 people are chosen, and I give that example of first place, second place, and third place. So if we're choosing first place, second place, and third place, or president, vice president, and treasurer, you know, then we would have 7p3, which is 7 factorial over 4 factorial. Okay. Now, if we want to make the same type of selection, except in a situation where the order or assignment of roles is no longer a consideration, then we have to realize that all of these groups of 3s that we're choosing, some of them are going to be repeats, right? And I give you an example there for first place, second place, and third place with Alice, Bob, and Charlie. So what we do is we want to cancel out or divide out all of the repeated groups of 3. Well, each group of 3, so let's say if you think about it this place, first, second, and third place, A, B, and C, you could have A, C, and B, B, C, and A, B, A, and C, C, A, and B, C, B, and A, right? So all of these would be considered distinct choices in a permutation, but they're actually all the same group of 3 in a combination, and so these are all going to be, well, I say double counted, they're going to be counted 6 times over, okay? And in fact, what it is each group, which has this many choices within it, is going to be repeated that many times, right? Because that's how many times you can switch these around, okay? And so what this ends up being then in a combination, if we were to just choose 3 people from a group of 7 and not assign them roles, not put them in any kind of order, we would take 7p3 and then divide out by 3 factorial to eliminate these repeats, okay? And so this 7p3 is again 7 factorial over 7 minus 3 factorial, and then the 3 factorial ends up in the denominator along with the 4 factorial. And so actually in a combination, you'll see that this and this number and this number always add up to the top number. I mean, they're factorial, so they're behaving a little bit differently, but you can always see that this and this will add up to that. And so the definition for a combination, if we go NCR, then that's going to be n factorial, n minus r factorial, and then we divide out by r factorial to eliminate those repeated choices. Okay. So, now that we've got that defined, let's take a look at some of the problems. So again, with these calculation problems, you know, you've got the feature on your calculator that will do these for you. I encourage you to work through them without the calculator and kind of see how they play out. If we've got 8C3, that'll be 8 factorial over 5 factorial, 3 factorial. So the 5 factorial will cancel out everything on the top except for the 8 times 7 times 6. On the bottom you've got 3 times 2, and there we go, 56. For 8 choose 5. Well, this is interesting because look at what happens, is that it's actually exactly the same thing. Okay? I remember I had a professor for, it was called discrete math, which is a broad area that includes permutations and combinations, and he was pointing out that if you are choosing 3 out of 8 things, then you are effectively at the same time choosing to not choose, you're choosing 5 things not to choose. And that's why these things always end up being the same. Okay, is the 5 and the 3. If the 5 and the 3 add up to be 8, then 8 choose 3 will always be the same as 8 choose 5. And the same thing goes for 8 choose 2 and 8 choose 6 will always be the same as well. It's kind of interesting, Pascal's triangle, if you've ever seen this, demonstrates that symmetry. Okay, you can see here and here that those numbers are going to be the same. Let's see, well, I'd have to go up to 8 to actually show this. I'm not really going to get there on the board, but you can at least see the symmetry in this. Pascal's triangle has a lot of interesting things going on. For one thing, in order to build it, you add these two together to get that one. And this is all built off of this definition as well, because, and it's also related to the, the coefficients when you expand a polynomial. Okay. So anyway, there's a lot of interesting things going on in Pascal's triangle. We won't get the time to talk about them this term, but it's certainly out there. Okay, let's look at a couple more of these calculation problems, and then we'll move in to the word problems. So let's see here. 6 is 18C2. So let's see, we're going to get 18 factorial, 16 factorial, and 2 factorial. So the 16 factorial will cancel out all the rest of that and just leave us with 18 times 17 over 2. 9 times 17, which I believe is 153. And then problem 8. Here we've got 9CR, and so the best we can do is just say that's 9 factorial over 9 minus R factorial times R factorial, and just leave it at that. Okay, problem 10, how many bridge hands of 13 cards are possible from a deck of 52 cards? Well, so in this case, it doesn't matter what order you receive the cards in, so long as they are the same 13 cards, and so this would be a combination for sure. And it would be 52C13. Now this is one that's good to use the calculator on, because I think that it's going to be a fairly large number. Let's see here, so 52C13. Yeah, it doesn't even give it to me, it gives it to me in scientific notation, 6.35 times 10 to the 11th, which I think is in the hundreds of billions. So, a large number. All right, let's keep going here. Yeah, a lot of these ideas of probability and permutations and combinations, well, probability in particular, come from mathematicians' consideration of gambling and card games. Things like, blackjack and roulette. These things were being played in, well, at least, I'm not clear, I haven't done a lot of reading about the history of that, but I at least know that, who was it? Well, I can't remember now who it was, but it was French mathematicians in the early 1800s that were developing these ideas of probability in order to determine what the probability of winning in these games of chance was. So the cards lend themselves to these ideas. And actually, if you look on Wikipedia, there's a listing of the probability of all the poker hands that are possible. And you can see that their probability is ranked in the same order that the hands themselves. So like a full house will be 3 of a kind because it's less probable. You're more likely to get 3 of a kind. That's why the less likely hand will win. Okay, let's see here. Problem 12, how many different bridge hands of 13 cards are possible if none of the cards is higher than a 10? So in problem 12, well, it depends on where you put the ace. If you put the ace low, let's see here, then you've got 40 cards to choose from, so it would be 40C13. If you put the ace high, then you're excluding it, and so you would just have the cards 2 through 9 in each of the suits, and it would be 36C13. Problem 14, if a person has 10 different t-shirts, how many ways are there to choose 4 to take on a trip, assuming that you're not planning the order in which you're going to wear the t-shirts, just selecting them to take on the trip with you, then it would be 10C4. This one, let's see, what would this come out to be? Just was curious because it's a pretty small number, and I was just wondering how easy it would be to calculate without the calculator. So there's 8, 3 into 9 goes 3 times, so that's 210. Okay, let's see what else now. Now we get into some more interesting problems. Problem 16, we've got 15 boys and 12 girls on a camping trip. How many ways can we choose a group of 7 to be selected to go out and get firewood with no conditions? Then the order of the selection shouldn't be important, shouldn't make a difference. We've got 27 people, and we want to choose 7 of them to go out and collect firewood, so it would be 27C7. So let's see what that comes out to be here. $888,030. Okay. All right. Part B. The group contains 4 girls and 3 boys. All right. So, and we're starting with 15 boys and 12 girls. 12. Okay, so if we want 4 girls from the 12, that'll be 12C4, right? And then, for the boys, we want to choose 3 out of the 15. Okay, and this gets multiplied in the same way that the fundamental principle of counting multiplies possibilities. This is the number of groups of 4 girls. This is the number of groups of 3 boys, and the ways that they can be put together multiplies them. Okay, let's calculate this and see what it comes out to be. Let's see here. So 12C4 times 15C3, 225,225. Okay, so it's considerably less, which makes sense, right? This will have more possibilities than this one is because this is a restriction. Okay. Part C is where it gets interesting. The group contains at least 4 girls. So there's a couple different ways to handle this at least problem. So that means at least 4 girls. So that means we're going to have this one, 4 girls and 3 boys. And then we're going to have 5, let's see here. At least, yeah, okay. Then we'll have 5 girls and 2 boys, 6 girls and 1 boy, and 7 girls. Now these are all or situations. They're not going to get mixed together in the same way that these did. We multiplied these because this was an and situation. We had these 4 girls and these 3 boys. And again, I mentioned it from the fundamental principle of counting, these got multiplied together. When you get these or situations, this is plus, okay? And so these are all going to get added together. Now, so one way that we can do this is to add these all together. So we'll take this one, 12C4 times 15C3, and then add 12C5 times 15C2, 12C6 times 15C1, this is just going to be 15, this one right here, 15 times that 12C6, and then just 12C7, okay? So that is going to be our answer. The other way to do that is to take the total number of possibilities and then subtract off, let's see here, not 12, 888,030. So take that 888,030 and subtract, let's see, all boys, 15C7, plus 6 boys and 1 girl, 5 boys and 2 girls, let's see here, 4 boys and 3 girls, and then that's it. Okay, the rest of these cases will have at least 4 girls in them. These are the ones that don't. Okay, so we should be able to get an answer from this, and then we should also be able to check that answer and make sure that it's the same as this minus this. So let's see if we can do that. It's a little bit heavy on the calculator work, but that's not the end of the world. All right, so 12C4 times 15C3, and then, let's see here, 12C5 times 15C2 plus 12C6, and then I'm just going to enter times 15, and then plus 12C7, and what is that? 323,037. Just as an aside, I find these problems tricky enough that I frequently do break them down, separate out the pieces, calculate the pieces, tally them all up, make sure that they add up to what we're interested, add up to what should be the total number. Or if we're doing something like this, I'll calculate both of these, see that they do reconcile. It's very tricky when you're working with this many different possibilities and how to interpret what's possible. Like I said, it can get very tricky. I once, when I was in grad school, I had a friend who was working on his PhD in agricultural economics, and his advisor's child was in like the 3rd grade, and the elementary school teacher asked them to make up a math problem one day, and so he did. And the math teacher couldn't solve it, didn't know how. He brought it to his dad, who was who had a PhD in agricultural economics. He struggled with it. gave it to his, my friend who he was advising for his PhD. I worked on it for a while. I brought it to a statistics professor that I knew. And eventually we did generate a solution. But what I'm saying is that these things are tricky. And a third grader can devise a problem that will set 2 graduate students and 2 PhDs working for over a period of a couple weeks to solve it. So that's why I go through this process where I calculate an answer and then I step back from it and try to, line everything out and calculate each piece separately and make sure that I'm doing it correctly. All right, having said that, let's see if I can calculate this, this part right here. All right, so 888,030 minus, let's see here, so we want 15C7, and then 15C6 times 12, 15C5 times 12C2, and then 15C4 times 12C3. Okay, let's see here. Then we want 888,030 minus all of that. 15C4, 12C3, 15C5, 12C2, 15C6 times 12, and 15C7. Yeah, 323,037. Excellent. Okay, so these are the same. Okay. Let's look at problem 18 here. This one's considerably more straightforward. We've got a group of 12 male and 12 female tennis players. We're going to choose 2 men and 2 women to compete in a men's versus women's doubles match. How many different matches are possible? Okay, so what we want is we want to choose 2 men from the group of 12 and pair them with 2 women chosen from the group of 12. And let's see what that's going to turn out to be. Let's see, I think I can do this without the calculator. This is going to be 12 factorial over 10 factorial, 2 factorial, or 12 times 11 over 2. Getting ahead of myself. There's only 1 6 there, and then when we multiply by 11, it's 66. So we just have to square 66, and that'll be 4,356. Okay. Let's see here. I think that's it for this section. So I'll post a quiz for this. And then also, I'm not going to make any more videos. If you want to go on into section 4.4, enjoy yourselves. That one is just sort of a wrap-up of the first 3 sections in chapter 4. It's a collection of problems that I've adapted from a variety of sources. And like I said, the problems themselves, I think, are interesting questions. Like I said, this one's going to be the last video. It's going to be the last quiz. The next thing I'm going to post is going to be the review for the final exam. As always, if you have any questions about any of this, including the project as well, please let me know. Thanks.